is a program that can use do while loop to your UC, right, will ask you to use recursion to solve it. That's the headache part. So no matter what, right, you need to get used to recursion, and no matter how much you dislike recursion, you also need to get used to it. Okay. What do you guys understand about recursion? Can somebody share me? Recursion means, right, when you write a certain function, okay, let's call this function as recursive. Example, we got a recursive, right? This function called as recursive. What we do is we call the function itself. Okay, we call the function itself, and this is called as recursive. Okay, normally you write your main method like this, right? And then what you do is you call a function. Okay, you call a function, but this time is a bit different. Okay, this time is a bit different. Write down in your note. Okay, write down in your note. Normally when we write recursive, we got two function. Okay, two function. When we write recursive, listen carefully. When we write recursive, we got two function. The first function is the real recursive. Okay, I repeat. The first function is the recursive function. Okay, recursive. You see the recursive, right? The recursive is calling itself. Okay, the recursive is calling itself. And then we got a wrapper. Okay, we got a wrapper. This is the second function. Almost all recursive should have a wrapper. And what is the purpose of wrapper? You may ask, what is the purpose of wrapper? But then if you Google what is the wrapper, right, you hardly can see it. That's why I tell you, don't skip lecture class. You skip lecture class, a lot of things, even if you want to Google, you might not able to see it. Okay, say you want to work with a company, you are not working alone. Usually you will work in a team. Please get used to socialize. That's one thing. Second thing, when you write a code, right, for other people, okay, when you divide tasks, say you are divided to write a recursive algorithm. Let me ask you, say if I am a programmer, my task is to write let's say decimal to binary. You still remember what is decimal to binary? This one. For example, in decimal, right, let's say 14, okay? If decimal 14, right, you convert it to 1110, okay? 1110. My job is to write this algorithm, okay? Let's say I have written a very, very good algorithm. Wow, so good, so beautiful, the code. All is commented. But the question is, when I submit this code to my leader, okay? Whatever title you call it, okay? Do you think he know what is the thing he need to be careful about? Okay? Example, I give you an example. In our binary, okay, say in this binary calculator, right? Binary calculator doesn't support negative, okay? So example, if I put negative 14, I'm not sure this support or not. Let me see. Negative 14. Cannot, okay? Didn't support negative. Okay, so let's say I write a binary algorithm. This binary algorithm doesn't support negative number. If I didn't put any checking, okay, I didn't put any checking. I just submit this code to, I know we cannot use negative in my algorithm. I'm the one who write the code. I know this limitation. My code doesn't support negative. If I submit this code, right, I submit this code to my lead programmer. Do you think he knows what to be careful about my code? No, right? Okay, no. Okay, even he is a very experienced programmer, because he is not writing the code, he don't know what is my limitation. Okay, he don't know what is the limitation of my code. Okay, example, my code may not support negative number. That's why you have to do the sanitization. Okay, sanitization in the wrapper. Okay, in the wrapper. The purpose of this wrapper is you need to do sanitization. Okay. Second purpose, when I write the recursive algorithm, right, okay, sometimes this is still very simple. Sometimes it's very difficult to understand. First thing is very difficult to understand. Second, it's very hard to read and maintain. I don't want to allow people to touch my recursive code. Okay, so what I do is I just write a wrapper. Okay, I write a wrapper. So the people who want to use my code, right, he don't touch this one. Okay, he don't touch this. So you notice, okay, if you can notice, right, when I write my recursive, right, I usually put a private. Okay, I put a private, especially in another class. If there is another class, imagine there is another class. Let's say I have a decimal to binary class. Okay, this recursive, right, usually we would put it as private. Okay, I put it as private. So other programmer would not able to see this recursive algorithm. What they see is they are exposed to this public wrapper only. Okay, when they want to use, they use the public wrapper only. Okay, this is the first thing. Okay, first thing. Second thing is to hide the complexity. Okay, second thing is hide complexity. I don't know which first or second already. Second is to hide the complexity. Say my recursive is very complex, okay? Only I am the one who know how to maintain it. Other people don't know. That is the reason. Okay, that is the reason why I want to use my wrapper. And third thing, in future, okay, in future, I noticed there is a bug, okay? I noticed there is a bug. The code in the main, right? Okay, the code in the main, my lead programmer, my leader, use the wrapper like this. So in future, when I need to fix the bug, right, okay, the lead programmer doesn't need to worry this. What is my job is, I only need to modify my recursive. Okay, example, in future, okay, in future, say if my output, okay, my console output, example, my console output is like this, 1110, okay, 1110. Okay, in future, I think this is not beautiful, okay, in future, I think this is not beautiful. I want to print it like this, 1110. In future, I say I want to print like this. My job is, I only need to modify here or modify here, okay. That is the purpose of wrapper. If you are not clear about this part, right, it's very hard for me to move on. The wrapper would have its own argument, okay. This argument would then pass to here, okay. So let's say I follow the input, okay, I follow the input. And then this input, right, we'll call this real recursive function, okay, recursive function. So if I print this, okay, if I print this, right, I print the quotient. Let's say I print the quotient from the argument, okay, I print the quotient. And then I call itself recursive. Recursive is equal to quotient plus 1, okay. If I want to print this, right, what do you guys think, okay, what do you guys think would happen? Will the program run? Will the program stop? Will the program crash? Or will the program not compile at all? Any idea? If you keep calling itself without stopping, what would happen is it will cause a stack overflow. Okay, as you can see, right, if you keep running, it will still printing some number up until one point. Okay, up until this number, right, you will see a stack overflow. Okay, you will see a stack overflow. Why do this happen? Okay, any idea what do this happen? As you can see, it keep printing number. It got keep printing number. It keep printing number up until 10367. Your stack has a limitation. Okay, your stack have a limitation. The code stack allocated for your Java program is roughly about 10 MB. One tiny, okay, tiny disadvantage. Okay, tiny disadvantage of recursive. So you need to be careful, okay, if you want to use a recursive algorithm. If you can use iterative, of course, use iterative will be faster. There's a few exceptions. A few exceptions where recursive is faster. Example, your quick stop. Heap memory, okay, heap memory is where you create an object. When you create an object, right, you listen only, your heap memory is to store the object and also the array. When you use the array or when you use the new keyword, right, it actually enter the heap memory. Heap memory, if I'm not mistaken, don't quote me, okay. If I'm not mistaken, right, heap memory doesn't have limitation. You can open as big as you want. So long your computer, okay, so long your computer have RAM, you can use heap open as big as you want. But the stack memory, right, stack memory usually have a limitation, okay. For example, the Java, it limit you to about roughly 10 MB only, okay. Just the side information only. Don't need to stress about this slide, okay. No need to stress about this slide. Extra info for you, okay. To prevent stack overflow, right, you know already you cannot keep calling the recursive. Let me show you the simple diagram. Let me show you a simple diagram. Okay, when you call this a recursive function, a simple explanation, if this is a recursive function, inside this function, right, I call the recursive itself, okay. If I call the recursive itself, right, this is example, okay, this is example, this is your RAM memory, okay. Let's say your RAM memory only have 5 position only, okay, 5, you look it at very simple, okay, a very simple level, okay. Let's say we have 5 location only. When you call the first recursive, okay, when you call the first recursive, right, you enter here, okay, the address enter here, the address enter here, and then because inside this function you call itself, right, then this recursive enter this location, okay. When this function enter this location, right, it will launch itself again, okay. It will launch this recursive, call itself again. So when it call itself, what happened when this 5 full already, okay. When this 5 full already, what happened is you get stack overflow, okay, stack overflow. Just a very simple explanation, okay, about stack overflow, okay. I hope this diagram is easier to visualize, okay. Okay, when you write a recursive algorithm, it's important you have a wrapper, okay, wrapper to prevent exception. And also when you write a recursive, you need to provide a stopping code, okay, stopping code. So example, okay, example, I want to limit this to print 5 times only, okay. If I want to limit this to print 5 times only, how should I do it? So I limit, if quotient, okay, if our quotient is less than, we start from what, 10, okay, we start from 10. Let's say I start from 1, okay, let's say I start from 1. So if I want to print it to 5 times, right, I use less than equal, okay? If our quotient is less than equal to 5, okay, then only I print the, okay, here is a harder question. Here is a harder question. Now, after I set a gut, okay, now I set a gut, okay? In this algorithm, right, I add one line of code, if statement. If our quotient, okay, if our quotient is less than or equal to 5, right, then only I execute this code, only I print the quotient, okay? Then only I call the recursive. Let me ask you, if I run this program again, if it cause any error, what is the order? What is the order? Do you think it's printing 1, 2, 3, 4, 5, or is it printing 5, 4, 3, 2, 1? Any idea? The answer is 1, 2, 3, 4, 5. Okay. So it's very important, okay? It's very important. When you write a recursive algorithm, right? Okay, you need to make sure your recursive have a stopping condition. Okay. This is a very important, okay, very important part. You need to make sure it got a stopping condition. Okay, stopping condition. This is very important, okay, very important. You need to make sure your algorithm have a stop condition. Okay. Now let me ask you all, if I put this print line, okay? If I put this print line downwards, okay? What do you think is the result? Is the result still 1, 2, 3, 4, 5? Any idea? Is it still 1, 2, 3, 4, 5? Or is it 5, 4, 3, 2, 1? Which one do you think it is? The answer is 5 to 1. If you don't believe, I run for you. Okay? The answer is 5 to 1. Oh, yo, amazing, oh. Why? Why? How come just now it's 1, 2, 3, 4, 5, and now become 5, 4, 3, 2, 1? Eh? What is the reason? Why? Wow, recursive. My head. Why? Why become 5, 4, 3, 2, 1? Why? What is the reason? Okay, the reason is like this. Okay, the reason is like this. You have a recursive function. Okay, when you have a recursive function, right, and then followed by a print. Okay, followed by a print statement. Okay, if you have a recursive function, then only followed by a print statement, right? This recursive function, okay, when you first launch this recursive, okay, when you first launch this recursive, there's a print statement here, correct? Okay, there's a print statement, but it will execute the code in here first. Okay, it will execute this code in here first. So this recursive will call itself, okay, it will call itself. When this recursive call itself, right, it enter here. Okay, this one from here, right, from here call itself, right, and then inside here there's another print statement some more. Okay, inside here there's another print statement some more, but this print statement will not reach. Okay, this print statement will not reach. Okay, I write like this better lah. Okay, I write like this better. Let me erase this. Okay, let me erase. Okay, this is say number 1. Okay, this is our number 1. Okay, this number 1, right, would be enter to this position. Okay, when this number 1 enter this position, okay, when this number 1 enter this position, it will call itself, correct or not? It call itself lah. It call itself. This is, let's say, number 2. Okay, let's say this is number 2. Let me use other pen color. Okay, let's say orange. Okay, this is number 2. Number 2 is will occupy here. This number 2, right, will execute the function like this also. Okay, recursive followed by a method. Okay, the method itself, and then followed by a call. Okay, and then it will execute a recursive. Okay, it will call itself again, and then only followed by the print. Okay, only followed by the print. So similarly, okay, similarly, when there's a print in here, okay, when there's a print in here, then the print would also wait in here, okay, wait in line. And from the second function, right, this is the second function. Our second function, right, in here, our second function also will call itself. Okay, also will call itself. Also will call itself, also have a print. But the first line to execute, the first one to execute is this one. Okay, so I use another pen color again. Okay, I use another pen color. Okay, let's use light green. Okay, so this is the third. Okay, this is the third one. So this third one, right, will spin in here. Okay, this is the third one. The third one will spin in here. It will call a recursive again. Okay, it will call a recursive again, and then followed by the print statement. Okay, let's say this is 3. Okay, 3. Let's go for 3 now. Okay, let's go for 3 now. Let's go for 3 now. Okay, 3. Okay, so when it reach 3, okay, when it reach 3, okay, there's another third like this. So there's another recursive. Okay, recursive. The code inside here, I'm talking about the code inside here. The code inside here is a third one. Okay, it's a third one. So there's other code in here also. Okay, other code inside here, other code. So this third code, right? This third code would 0. If our quotient is less than equal 3, we still call the recursive. We still call the recursive. Okay, we still call the recursive. So what would happen is, okay, so what will happen now? Okay, it will open. Okay, it will open another again. Recursive. It will call the recursive function again. Okay, call the recursive. And this is the fourth one. Okay, when we enter the fourth one, okay, when we open the fourth one, right? Okay, we open the fourth one, then we see is the quotient less than equal to 3? Okay, the quotient okay, the quotient in here. The quotient is 4. Okay, the quotient is 4 right now. Here the quotient is 4, okay, the quotient is 4. If the quotient is 4, right, we will not execute this code, okay? This if statement code, right, will not execute, okay? This 4 will not execute, okay? This 4 will not execute. So we didn't do anything, okay? So the 4 can close away already, okay? 4 will close, okay? And this 3 recursive, will open the fourth one in here, okay? You will open the fourth recursive. When this end, right, when this end, then only what? Only it print, only then it print, okay? Only it print the quotient, okay? Only it print the quotient, okay? Let me use the final color, which is red color, okay? Only then it print the quotient, become 3, okay? It print the quotient, I should have opened it side by side like this, okay? When it print the quotient become 3, then it exit this function, okay? Exit this function. So our 3 is also destroyed, okay? 3 is destroyed. Just now, okay? Just now our 2 is execute this one, okay? And then when this is destroyed, right? Then we reach the next line of the code, okay? This next line of the code is also printing, okay? Printing. So we print 2, okay? We print 2. And then when we finish execute, okay? When we finish execute already, then the 2 can end, okay? The 2 can end already, okay? When this, by the way, this code is actually calling the 2, okay? So when our 2 close, right, then we can execute the last line, okay? Last line of code, which is printing the 1, okay? So as a result, right, what you see in the terminal is actually 321, okay, 321. Can understand? Can understand why it print 321? But this will make more sense. So there's a orange code in here, and then this is a third one. The third one is the green color code. So it's a recursive, right? And then this actually is the recursive. And then our second color will be green, the green color recursive. And then the green color recursive, they have a blue color. So this one is actually a blue color. Like this is better. This is a dark green. The blue is a dark green. We call the first recursive, right? When we first enter this function, okay, when we first enter this function, right? So we enter here, okay, the first one is in here. Okay, the first one in here. Then in this code, right, inside this first function, okay, inside this first function, there is 2 lines of code, which is recursive and print, okay, which is recursive and print, okay. This recursive will open the second one, okay, open the second one, okay. In this second one, right, there's also a recursive and also a print also, okay. So you can see there's a recursive and print in here also, okay. This second, okay, inside this second function, there's a recursive, okay, the third one, okay, the third one. So we will spin another, the third one, okay, it will spin the third one, okay, this is the third one. Inside this third one, right, there is also a recursive and also print also. Recursive and print also. So in the third one, right, the third one will actually spin a recursive again. Okay, it spin a recursive again, and then when you reach the quotient, okay, when the quotient is more than it's not less than equal 3, okay, when it's not less than equal 3, right, then we exit it, okay, then we exit it. When we exit this function, right, then we come back, okay, we come back from this code, okay, we come back to this code, then we execute the next line, we execute the next line, okay, we execute the next line. So that's why you can see 3 in here, okay, 3 in here. After we print this number 3, okay, after we print this number 3, right, then this function end, okay, this function get crossed out, okay, this function end, right, okay, we print the number, okay, we print the 2, okay, we print 2 in here, okay, and after we print the 2, the function end again, okay, the function end again, we cross this, then we lastly, we get this print, okay, we get this print, so that's why we print the number 1. Is this okay? Is it more clear? Can I move on? You need to understand this one, okay? If you got any question, please tell me. This concept is super useful, okay? Super useful. You need to able to visualize this, okay? You need to able to visualize this so that it can help you to code, okay? So that it can help you to code in future worksheet, okay? As I told you earlier, some code is not available in Google, okay? So sometimes you need to write your own code. Now we are going to look at the wrapper, okay? The wrapper, right, will handle the exception, okay? As example, in my binary recursion, say if my binary recursion doesn't support negative number, okay? If my binary recursion doesn't support negative number, right, what I need to do is I need to handle, okay? I need to handle exception in here. How to handle it? I roughly show you, okay? If our input okay, if our input is less than 0, okay, if our input is less than 0, right, we need to say example, we throw a illegal argument exception, okay, we throw and then followed by a string, okay, followed by a string. Example, the binary converter doesn't support negative number, like this, okay. If the input is not less than 0, else, okay, else, then only we call the recursive function, okay. So this is how we do the sanitization, okay, sanitization. Is the input less than 0? If input is not less than 0, okay, then only we execute the recursive, okay. Understand? Okay, understand? Okay, we handle the exception in here. Okay, we handle exception in here. Okay, understand? So if, okay, if other people go and use our code, right? If other people use our code, let's say he put negative 10, okay? So he put negative 10, right? He will see the exception, okay? He will see exception. So the people who want to use this code will know like you need to use a try catch. So I run this for you. Okay, I run this for you. So you can see, okay, you will see a illegal argument exception, okay? This message, okay, with this message, okay? Can understand? By the way, right, for your worksheet, the binary converter, right, is a very good practice, okay? Very good practice. Please don't look at the code online, okay? Don't go and search for the code online. The recursive is like the easiest practice. So please try and run your, it will truly help you to think, okay? Think deeper about recursive. It helps you to truly understand the recursive. Please go and write it yourself, okay? Don't go and Google. After you finish the code, then only you go and Google, okay? Okay, let's talk about exception. Okay, let's talk about exception. If you want to put a try catch, right, usually, okay, usually you also put inside the wrapper also, okay? You also put inside the wrapper. So if, let's say, I think this is quite stupid, okay? I think this is quite stupid. But if somehow, okay, if somehow there is other exception, right? If there is other exception, you use the try catch inside here, okay? You write the try catch inside here. Then only you move the code, okay? You move this entire code upwards, okay? You move the entire code upwards, okay? Like this, okay, like this. Maybe right now you don't need to throw and then catch. This is a bit stupid, okay? This is a bit stupid. This one, right, if you think it's not necessary to throw an exception, okay? If you think it's not necessary to throw an exception, you can simply print it line. I need a print line, I think. I need a print line like this, okay? Now let's go and look at exception, okay? Let's look at exception. In the exception, right, actually our Java got a few hierarchy, okay? We got a few hierarchy. The object, right, object is like the parent, okay? Object is like the parent of every Java class, okay? Object is the parent, okay? Object is the parent. And then our throwable, okay? Our throwable inherit, okay? Inherit our object. And then the exception will inherit the throwable. IO exception will inherit this one. And then found will inherit this one. When you write your try catch, okay? When you write your try catch, listen carefully, when you write your try catch exception, it's very important, okay? Very important. You catch the child first, okay? It's very important you catch the child first, okay? Example, this is file not found, right? Okay, file not found. It's very important you catch the file not found and then only catch the IO exception. Okay, IO exception. After you catch the IO exception, then only you catch the more general one. Okay, general one. Remember what I said today. Okay, remember what I said today. This is very important. Okay, this also determine how strong is your coding skill. Okay, this is a very basic thing. Okay, very basic thing. Don't make this type of mistake. The most general one. Okay, the most general always starting at the most bottom. Okay, starting at the most bottom. By general, I mean the parent. Okay, usually the parent is the most general one. Okay, the parent. The order is important. Okay, the order is truly very important. If you catch the exception, okay, if you write this exception upwards, okay, if you catch the exception like this, example, if you want to catch an IO exception, maybe I catch a file not found, okay, if I catch a file not found, if I put it in the bottom, okay, if I put it in bottom, right, supposingly, I want to print, okay, the file you enter is not found. The file you've chosen is not found, okay. Supposingly, if I expect I would receive this message, however, because you catch the exception in here, when there is a file not found exception, okay, when you run this code inside here, okay, when you run the code inside here, if there is a file not found exception, right, what will happen is it will enter here, okay, it will enter here, it will enter this line. So what happens is this code doesn't get executed anymore, okay, this code doesn't get executed anymore. So you need to be careful, okay, you need to be careful. The order is very important, okay, the order is very important. So what you need to do is you need to move the catch, okay, move the catch downwards, okay, move the catch exception downwards here. So right now, if there's a file exception, okay, if there's a section, then only it will print this one. Okay, it will print this. You get what I mean? When we can reuse recursive. I tell you the answer now. Okay, I tell you the answer now. Because if I keep asking you, you may get tired. Okay, your brain may get tired. There are two scenarios we want to use recursive. The first one, okay, the first possibility where we can use recursive is when the pattern is repeating. Okay, when the pattern is repeating. Then you may ask, what do you mean by the pattern is repeating? Example, I convert decimal to binary. Okay, let's say I convert decimal to binary. So to convert decimal to binary, right, let's say 13 divided by 2 is 6. Then we get remainder as 1. Then I divide by 2 again. Then I get remainder as 0. Then I divide by 2 again. Then I get remainder of 1. And then I divide by 2 again. Then I get remainder of 1. Okay, so I need to read the binary in this direction. Okay, I read the binary in this direction. If I keep repeating divided by 2, if I keep repeating divided by 2, if I keep repeating divided by 2, okay, as you can see, if the pattern is repeating, then you can use recursive. Okay, you can use recursive. And second, when is the time then we need to use recursive? There is the time we need to use recursive, especially when we want to explore all the paths. Okay, when you want to explore all the paths. Okay, this is particularly very useful. Okay, very useful in the recursive algorithm. It's so hard. Okay, truly very hard to use an iterative algorithm. Iterative algorithm mean this one. Okay, iterative mean this one. Use an for int I equals 0 I is less than length I plus plus okay. This is called as iterative algorithm. Sometimes right, we cannot just use for loop. Okay, we cannot use do while loop. We cannot use while loop to solve it. Okay, sometimes it's just too hard, really too hard to solve using iterative. Okay, remember last week I told you about the graph chord. Okay, example we got A, B, C, D path. Okay, the distance of AB is 1, BC is 2, AC is 4, AD is 3, DC is 2. Let's say, okay, let's say if I ask you what is the shortest path? Okay, I ask you what is the shortest okay, I ask you what is the shortest path. It's very difficult. Okay, it's very difficult if you want to use iterative. Okay, very difficult if you want to think using iterative to find the shortest path. Okay, because there can be a lot of path. Okay, a lot of path, and that's why you want to use an recursive. Okay, recursive you keep go left, go right, go left, go right, go left, go right. Okay, until there is no more path. Then we can count the distance. Okay, we count the distance. ABC is 3. Okay, ABC is 3. And then AC distance is 4. And then ADC is 5. Okay, after we done using a recursive, then we know, so this is the shortest path. Then you can tell me, ABC is the shortest path. This is the place where recursive is very strong. Okay? So strong. It's so strong. And also recursive, okay, recursive can break down problem. Okay, break down problem into a smaller part. Okay, this is also the strong part about recursive. Example, in your quick sort and I forgot quick sort or merge sort. I think it's a merge sort. Merge sort is actually break down the problem becomes smaller and smaller, then only perform a sorting. This part is what makes recursive smaller. When you reach next chapter, right, you will see merge code is so fast. Okay, faster than insertion sort. But we talk about that in future. Okay, there are also disadvantage of recursive. I'm not saying it's a perfect solution. There is also a disadvantage of recursive. What is the disadvantage? Okay, there's actually an overhead. Okay, there's an overhead. What do overhead mean? Overhead mean bottleneck. Okay, bottleneck. NECK. Okay, bottleneck. There's a bottleneck. Bottleneck. What do bottleneck or overhead mean? Okay, when you call a function. Okay, when you call a function, right, there's actually a bottleneck. If I say there is a bottleneck, can you guess what is the bottleneck already? Bottleneck mean there is a slight delay. Usually the bottleneck, okay, set by your lecture slide, not set by me, okay, set by your lecture slide. The bottleneck can be quite tiny, okay, the overhead can be quite tiny, so you don't need to care about that, okay. When you call the recursive algorithm, okay, when you call itself, right, this process is not free, okay, this process, right, keep calling function. This process actually takes some time, okay. In the perspective of computer, right, there is actually a latency, okay, there's a latency, like example, a few milliseconds to open a new process, a new function, okay, a few milliseconds to open a new function, okay, this is a tiny bottleneck. Second thing, recursive can be quite dangerous, okay, in term if you didn't think carefully. So you always need to think carefully, okay, when you write a recursive algorithm. But nothing to worry, okay, you will know there is something wrong with the code, okay. You will know something with your code if you didn't write a stopping condition, okay. This is the tiny part about the recursive, okay. If your program, okay, if the problem you solve, not saying dangerous, dangerous is just a tiny problem. With a careful, okay, with a careful decision, you can also eliminate, okay, you can eliminate the dangerous part. But the second disadvantage mainly is about stack overflow, okay, stack overflow, okay, stack overflow. This is the part where recursive is having disadvantage. Example, in our graph algorithm, okay, if our graph algorithm, if you see a graph which is tiny, okay, this graph is quite tiny, right? You probably will not see, okay, you will not see stack overflow, but as the graph, okay, as the graph become more and more complex, okay, so complex, so complex, so complex, okay, so many travel paths, okay, so many travel paths, so many paths, so many paths, so many paths. Then you need to evaluate all the possibility of the path, okay. For example, using recursive, right, you can actually possible to cause stack overflow. In fact, right, last time I benchmarked my recursive algorithm, because when the code is too complex, right, you can get stack overflow also, but it's very less likely at your level, okay, at your level it's very less likely you can meet a stack overflow, okay, because the question given by your DSA usually is still relatively simple. I said relatively, okay, relatively simple. I didn't say simple, okay. I know it's hard. Now, let's go and look at the essence of recursive algorithm. This is the general structure of recursive algorithm. If you want to write a recursive algorithm, right, this is the pseudocode, okay, this is the pseudocode. Example, our method name is called as recursive algorithm, okay, and then this is the parameter, okay, this is the parameter, and we want to return the result, okay. So in the first scope, like the last week I told you, right? Like last week I told you, we handle all the possibility of error at the top first. Okay, we handle all the possibility of error at the top first. Okay. Example, if we want to stop it, okay, then our result is equal to something. Okay, like this one. Okay, like this one. Okay, like this like this one. If I decide to stop in here, okay, if I decide to stop in here, then I write the stopping code first. Okay, I write the stopping code first. You are not just writing like this. Okay, you are not writing everything in here. Okay, you are not writing everything in here. Usually you have a wrapper first, okay? You need to pass through a wrapper first. Your wrapper would have a stopping condition also. Example, if my input is less than 0, right? If the person trying to use decimal to binary algorithm, okay? Example, if the input is less than 0, I don't want to allow him to proceed. So what I should do is I print the message first. I stop him first. Okay, this is the part this is the general part of this recursive law. Okay, the take-home message for you is stop condition first. Okay, stop condition first. Then only we write the recursive algorithm. If you keep following this standard, right, you will play very safe. Okay, play very safe. Okay, just follow. Okay, just follow this formula. Okay, so let's look at a factorial. Okay, remember what is a factorial? Example, this is a 3 factorial. Okay, 3 factorial means 3 multiplied by 2 multiplied by 1. Okay, this is a 3 factorial. Okay, 3 factorial. Now let's look at this code. Okay, this code is from your lecture slide, except I modify something. I add a print in here. Okay, so I have a call and factorial. This is using recursive to solve it. Okay, recursive algorithm. Okay, the recursive algorithm, right, will take in a int n. Okay, int n. Okay, so you call the calculate n factorial like this. Okay, if you want to count 3 factorial, you write 3 in here. Okay, this is the n. Okay, the n here. Okay, so let's see what is the code. Let's explore together. Initially, right, the code declare the factorial variable and initialize. Okay, initialize as 1. Okay, initialize as 1. So you need to write a wrapper. Okay, you need to write a wrapper, not like this. Okay, not like this. If our n is less than 0, okay, if our n is less than 0, right, then we throw a illegal argument exception. Okay, we throw illegal argument exception because there is no negative factorial, right? Because let me use another pink color. You don't have a negative 3 factorial. Okay, probably there is, I don't know, but our algorithm doesn't support negative 3 factorial. That's why we provide a terminating condition first. Okay, we provide a terminating condition first. Okay, if we need to stop the code, then we example, this code is using a throw new illegal argument exception. If you don't want, right, you can use system.out.printline also. Okay, you can print the exception also. So this code is actually using a illegal argument exception. Okay, so he say import must not be negative. Okay, so far so good, right? And then if our n is equal to 0, okay, if our n is equal to 0, this part out, okay, starting from this part needs to be inside factorial. This part will need to be inside recursive, okay, this part to need to be inside recursive. But this part n less than 0, this n less than 0 supposed to write in your wrapper, okay, n less than 0 supposed to write in your wrapper, okay. I repeat again, okay, I repeat again. This n less than 0, right, this n less than 0 supposed to write in the wrapper. This part need to write in the wrapper. This n equals 0, you need to write in the recursive, okay, because this is the stopping condition, okay, stopping condition for the factorial, stopping condition for the recursive, okay, stopping condition for the recursive. If our factorial is equal to 0, okay, n is equal to 0, right, then we return, okay, we return S1, okay, we return the S1 because 0 factorial is equal to 1. Okay, 0 factorial is equal to 1. So this is the code now. Else, okay, if n is not 0, okay, if n is not 0, right, then only we do the algorithm. Factorial is equal to n multiplied by calculate n factorial n minus 1. Okay, so we keep calling it, no? Okay, so far can you understand this code? Can you understand this code? Before I proceed to the diagram, can you understand this code? Let's say I call a calculate n factorial recursive. Okay, I call a calculate n factorial recursive, right? I start from 3. I want to achieve this result. Okay, I want to achieve this result. 3 multiplied by 2 multiplied by 1. Okay, so I call a 3 function. Okay, so I call 3 first. I call a recursive 3 in here. Okay, I call a recursive 3 in the stack. Okay, you can imagine a stack like a bottle. Okay, you can imagine a stack by a bottle. When you want to fill in the bottle, right? When you want to fill in the bottle, the most bottom one, okay, the most bottom one get filled first, correct or not? Okay, the most bottom one get filled first. Okay, you can imagine the stack like a bottle. Okay, you can imagine the stack like a bottle. So when we call the recursive of 3, okay, when you call the recursive of 3, right, let's go and explore the code. Is our n less than 0? Our n is not less than 0, right? Okay, our n is not less than 0. Is our n is 0? Our n is not 0 also. Okay, our n is not 0 also. Then we enter here, we enter here again. Okay, so we call a recursive again. So in our recursive, okay, our recursive is 3 minus 1. Okay, 3 minus 1. So 3 minus 1 will be 2. Okay, 2. So we got another recursive. When you call 3 minus 1 is 2, right? This 2 will call itself again. Okay, this 2 will call itself. It will enter this stack. Okay, it will enter this stack. Okay, this print doesn't get executed yet. Okay, this print doesn't get executed yet. This print is still in pending. Okay, this print is still in pending. Okay, this print is still in pending. Okay, waiting. Okay, waiting because this line will need to be executed first. Okay, this line will need to be executed first. Then our n is actually 2. Okay, 2 multiplied by n minus 1. 2 multiplied by n minus 1, right? This become recursive 1. Okay, recursive 1. Then we call a recursive 1. Okay, we call a recursive 1. Okay, we call recursive 1. In recursive 1, right? Recursive 1, recursive 1. In the recursive 1, is n less than 0? Is 1 less than 0? Okay, is 1 less than 0? No, right? No. Okay, is n is equal to 0? N is not 0, right? Else, our factorial is equal to n multiplied by our n minus 1, which means 1 minus 1. Okay, 1 minus 1 is 0. Okay, 0. Then we call another function again. Okay, we call another recursive. Okay, recursive 0. Okay, then we go to recursive 0. Okay, recursive 0 in here. If is our n less than 0, our n is not less than 0. Our n is not less than 0. Else, is our n is equal to 0. Okay, if our n is equal to 0, right? Our n is equal to 0. Now n is equal to 0. Then we return the factorial as 1. Okay, we return the factorial as 1. Okay, we return the factorial as 1. Now let's use another color. Okay, we return the factorial as 1. Okay, so this function officially terminated. Okay, terminated. So this recursive 1, right? Recursive 1 is actually 1 already lah. Okay, it's 1. Okay, return function is 1. So n is what? N is here 1. So 1 multiplied by 1. Okay, 1 multiplied by 1. Actually here. Our n, the full formula is like this. N multiplied by recursive. Okay, n multiplied by recursive. N multiplied by recursive. Okay, n multiplied by recursive. So our n, okay, our n is 1. 1 multiplied by the return. Okay, the return is 1 just now. So 1 multiplied by 1. Then this is, we get the result of 1 also. Okay, we get the result of 1. Then we print the n. Okay, we print the n. Okay, that's why we receive a 1 in here. Okay, we print 1 in here. Okay, and then right after this function close already, then we come to here. Okay, we come to here. Our n is what? Our n is equal to 2. Our n is equal to 2. 2 multiplied by the return value. Okay, the return value is 1. Okay, 2 multiplied by 1 is equal to 2. Okay, this will produce 2. This will produce 2. And then right, the print statement, I should use the blue color. Okay, the print statement, right? The print statement will actually print 2. Okay, print statement will print 2. So this will actually close already. Okay, this close already. Okay, this 2, right, will be returned. Okay, return to here, return to this function. Okay, so this one, right, this one is actually our n is what? Our n is 3. Okay, our n is 3. Our n is 3. So 3 multiplied by the return statement. Okay, the return statement is 2. 3 multiplied by 2 is 6. Okay, so you get 6 in here. So this also n. Then only finally you print the n. Okay, then you print the n, then this one is actually 3. Okay, so this is how the recursive work. Okay, this is how the recursive work. If you are executing the code, right, you can actually track it by this. Okay, you can actually track the result like this. When you start in the recursive, right, always draw out the diagram. Okay, draw a diagram so you know where went wrong. Okay, where went wrong. Can understand? So we achieve the result 1 multiplied by 2 multiplied by 3. A bit advanced. This topic. Understand this part? You truly need to understand this one because later you need to print the Tower of Hanoi. When you print the Tower of Hanoi, right, you need to add the indentation. Okay, you need to add the indentation. The algorithm already give you. Okay, the algorithm give you the code already. Okay, the algorithm give you the code, but to add the indentation, okay, right, you need to understand this one. Okay, you need to understand this one. That's why I teach you this one. Can, but sometimes it's not can, sometimes but no, it's not very viable. Sometimes it's not viable. Example in the graph algorithm. If you write using recursive, right, maybe 1,000 line of code you can finish. Okay, example only. If you write using recursion, maybe 1,000 line is finished already. But if you write using iterative, right, you might need 6 pages of code. 6 pages, listen carefully. 6 pages of iterative code. A bit tedious. Example this factorial. Okay, example this factorial. This factorial actually suppose we can actually do it using a for loop. We can do it using for loop. Using for loop we can solve this one. But this example want you to use recursive. So you use recursive. Okay, can I proceed? How this n-1 work? N-1 because you need to, when you want to count 3 factorial, right? Okay, when you want to count 3 factorial, when you initially you launch a 3, you call a factorial recursive 3. Okay, you want to use 3 multiplied by, okay, you want to use 3 multiplied by something. Okay, -1 okay, -1 3 multiplied by -1 so you -1 in here. You write the formula -1. So when you call itself again, then you call -1. Then you call -1, and then you call -1 again. This is why we -1. Understand? Any more question? If for question, you need to tell me. Okay, please don't let it accumulate. Okay, don't let it accumulate. If you got question, please ask me. Better we clear it first before we move on. Okay, I told you already. Okay, why do we need to handle error in wrapper? Because next time you are working in a team. Okay. Lastly, I want to share with you is about the Tower of Hanoi. Okay, if you play a Tower of Hanoi, right, if there's a 3 block, okay, right, you can use a repeating pattern. Okay, you can use a repeating pattern to arrange it, okay, to move it. If there's a 3 block, then you use a 3 block way, okay, use 3 block way to move to the third rod. Okay, this is the rod, ROD, rod or peg. If there's a 4 block, okay, right, then you use a different type of pattern, okay. If there's a different type of pattern, then we can use the different type of pattern. The pattern is fixed, okay, The difference is just between odd number or even number. Okay, odd number or even number. So this Tower of Hanoi, right? I don't know who is this person. This person is truly so smart. So smart. Okay, so smart, so genius. Okay, he come up with a recursion algorithm. He found out. Okay, this person is so smart. To be real honest with you, until today, right, I didn't truly. If you ask me to write a recursion algorithm of Tower of Hanoi from scratch, okay, if you ask me, don't look at the code of the Tower of Hanoi. I can tell you, I cannot code it. To be honest with you. Because I don't even know what is the pattern. Okay, I cannot figure what is the pattern. But someone so genius, they figure, okay, someone so genius figure out the Tower of Hanoi is just a pattern, okay, a repeating pattern. a repeating pattern to move the block. So this person, okay, this person go and write a recursion code. Go and write a recursion code. If our n is equal to 1, then blah blah blah. Else, then blah blah. Like this. So this is the recursion algorithm. Okay, you can follow the slide. Okay, you can follow the slide recursion algorithm. I can assure you this code is correct already. Okay, this code is correct already. But the lecture slide code naming is very bad. Okay, naming is very bad. The move this, right? This function is actually performing a printing. Okay, performing a printing. Okay, this is the lecture slide code. With that, I have finished cover what I want to cover today. Practical 2 will ask you to write a factorial and Fibonacci. To be honest, okay, factorial, right? Factorial, you can write it yourself. Okay, you don't need to Google. Factorial is relatively easy. Okay, relatively easy. Like try to blindfold yourself. Even if you already see the code. Okay, sure. Go ahead and see the code. Sure. See the code. But after you see the code, right, I would advise you blindfold yourself. Okay, don't say blindfold. Don't refer to the code. Okay, don't refer to the code. Try to write yourself the factorial code. You need to able to start from the beginning. Okay, you need to able to start from the beginning. Need to jumpstart. Need to jumpstart yourself. So try to write the factorial code by yourself. Okay, don't look at the slide first. Okay, don't look at the lecture slide one. Okay, try to write yourself if possible. Okay, and the Fibonacci is a bit advanced. Okay, a bit advanced. If you refer the lecture slide, I don't blame you. And then right, the GCD is the hardest one. And then right, you have number conversion. Okay, you have number conversion. Number conversion, right, you can also write it using recursion. Okay, you can write it yourself also. Okay, for this worksheet, right, I would advise you need to try to blindfold yourself. Don't refer to the code. Okay, don't refer to the code. Try to write out yourself. Factorial and number conversion. Okay, it's very possible. Truly very possible. Write the number conversion by yourself. Okay, truly very possible. The number conversion is just now what I told you. Okay, just now what I told you. This one. Okay, this one. Example, we want to convert 16 as base 10, right? 16 convert to base 10 in binary form. So you use 16 divided by 2. Okay, 16 divided by 2, 16 divided by 2, 16 divided by this one is add, sorry. And then you divide by 2 again. Then this is 4. Then you divide by 2 again. This one is 2. Then you divide by 2 again. This one is 1. And this is, I didn't write the remainder. Or 0, 0, 0, 0. And then this one is 1. Okay, then you divide by 2, 0. Okay, so you read you don't need to read. Okay, you don't need to read. You can direct print. You can direct print the what you call you can direct print the result. Okay, you can direct print the result. Number conversion is truly very possible. So I will advise you, right, even if these two you refer to Google, or if you translate from pseudocode from the lecture slide, I will advise you try to write the factorial and number conversion by yourself. Okay? Because the number conversion I truly write by myself. Okay, I've written the recursion code by myself. I know it's manageable. Okay, so try to write it by yourself. Factorial I also write it by myself also. So I know it's manageable. So if I can do it, you can do it also. Okay, you truly can do it. Okay, you truly can do it. So please try and write yourself. Okay.